Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and this video is part 2 of proving trigonometric identities. In the previous video, we took a look at some basic identities, which I'll review briefly, and we also looked at what was involved when you were asked to prove an identity. So you're not solving an equation, a common mistake. You're just focus on one side of the identity and manipulate it with basic identities and some algebraic techniques until it looks exactly like the other side. It doesn't matter which side you work with, just pick one. And some of you will take longer to get to the end result than others, which is fine. Everybody can see things differently, and there's often numerous options for when you're asked to prove an identity. I'm going to try to do what I think is the easiest and quickest way, but you might see a technique that would be more suitable for you. So the beauty of doing identities is you always know what the answer is. You always know what you want to end up with. So let's talk first of all about our basic identities that I introduced in the last video. Basically, these are definitions of these trig functions that we talked about when I first started talking about the definition of the trigonometric functions. The next three are similar to these three, just written a little bit differently. Basically, know which function is the reciprocal of which function. Then in the last video, I showed how these identities were true. And then these last three are called the Pythagorean identities, and I showed where they came from. So these are the 11 identities we're going to use, as well as some other techniques that I'm going to show as we get into different examples. Have this sheet in front of you when you are doing identities, so you're not having to try to memorize everything. I mean, it's quite possible you'll need to memorize them for an exam, but even in that situation, what I would recommend is when you start your exam, take a few minutes to write down your identities so that they're right in front of you, and it will make it easier when you're doing your proofs. Okay, let's get started with some examples. All right, we're going to start with our first example. The instructions you'll typically see when you're doing these questions are prove the given identity. I mentioned in the last video that I typically start with the longer or the more complex side and try to simplify it to the shorter or simpler side. So that means I'm going to try to manipulate this so that it equals this. And one of the strategies that I mentioned in the last videos that's often helpful is to write everything in terms of sine and cosine. So that's what I'm going to do. I'm going to replace cosecant with 1 over sine. So cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. I'm dividing a fraction by a fraction, so I can take the steps to go 1 over sine theta divided by 1 over cos theta. Or we could have gone straight into 1 over sine theta times cos theta over 1. That gives me cos theta over sine theta. And I know that cos theta over sine theta is equal to cotangent theta. Once this is exactly the same as the right-hand side, I'm done my proof. In my next example, I'm going to look at using something else. Whenever you see terms that are squared, probably, not always, but probably you're going to be using one of your Pythagorean theorems. Just take a look to see if that's going to work. That's not always going to be true, but in this case it certainly is, and it often is. So sine of x, I'm just going to leave that alone. And I'm going to take this complicated side and make it look like this, because it's much tougher to take that and make it look like this. So we're going to simplify here. I'm seeing 1 plus cotangent squared x, I'm going to look at my Pythagorean identities, and I have one that says cotangent squared theta plus 1 is equal to cosecant squared theta. That's the one I'm going to use. So this is equivalent to cosecant squared x. Now I'm going to use my strategy of writing everything in terms of sine and cosine, in this case in terms of sine. So cosecant theta is equal to 1 over sine theta. So cosecant squared x will equal 1 over sine squared x. Sine of x, if we're multiplying fractions, remember it's over 1 times 1 over sine squared x. I can cancel a factor of sine of x in the numerator and also in the denominator. So when I cancel or divide a sine of x into sine squared x, I'm just left with sine of x. So that simplifies to 1 over sine x. And 1 over sine of x, we know, is cosecant of x. Once you have an expression on one side of your proof that's identical to the other side, you're done. Okay, the next example, again, I'm going to work with this side and try to make it look like that. I have some squares, so I'm going to take a look to see if I can use my Pythagorean identities. We know that cos squared theta plus sine squared theta is equal to 1. Therefore, you can do a couple of things. If you can see that by subtracting sine squared from theta of both sides, that's going to equal cos squared theta. So if you can recognize that this is cos squared theta, you can plug that in. Or if you don't recognize that, replace 1 with cos squared theta plus sine squared theta. So instead of a 1, I'm going to write cos squared theta plus sine squared theta minus sine squared theta. So if you can recognize that that's equal to cos squared theta, because all we'd have to do is subtract sine squared theta from both sides, you can go right to this step here. So cos squared theta plus sine squared theta minus sine squared theta is just simply cos squared theta. So it's really up to you how many steps you feel that you need to take. Just don't take too many steps and do too much in your head, because then it's not a proof. We're not racing to an answer. We already know what the answer is. We want to see the logical steps to get there. I'm going to write secant in terms of cos, so that's going to be 1 over cos. And then this will be cos squared theta over 1. I can cancel a factor of cos theta out of the numerator and the denominator. And when I do that in the numerator, just one of the factors disappears. So I'll have cos theta over 1, which is cos theta. And the proof is done. In this next example, I'm not going to have all my identities on the board. Hopefully you've got a sheet in front of you so you can refer to that as I mention them. And in this example that we're going to do, it's debatable which side would be easiest, but I'm already seeing a way to simplify this side. So I'm going to start there. With identities, just start. If you get stuck, then you start again, but just try things. You know, the first thing you try isn't always going to work, your first strategy, but just try other strategies until you get something that gets you the desired result. So if I start here, I know what my answer needs to be. So what I'm going to do here, because this is a squared factor, cosecant squared of x, I'm going to replace that with one of the Pythagorean identities. So I'm just going to call this left-hand side. I don't want to have to write that out every time. I'm going to leave tan x alone for right now, because I may want to write it in terms of sine and cos. I don't know yet. I'm probably not going to. I'm not really going to need to in this example, but just wait until you get to a point where you get stuck. What I want to focus on is what cosecant squared of x is. And if you look at your Pythagorean identities, this will be equal to cotangent squared of x plus 1. I'm taking a often when I'm doing my identities, I'm looking to see where I'm going. Okay, this is where I'm going. So I'm just going to change the order of those two terms. And if you would have written it like that initially, that would be fine as well. I'm just showing all my steps so I don't lose anybody. Now what I'm going to do is I'm just going to multiply that through. So I'm going to get tan of x plus tan of x times cotangent squared of x. Now, this is squared, but I'm not going to go back to my Pythagorean theorem, or I'll just be going around and round in circles. What I am going to write that in terms of is tan, because I'm looking at, I've already got this term that I want. Now I want this term. So if I write that as 1 over tan squared of x, I can simplify this. Tan goes into the numerator once, into the denominator tan of x times. So I'll have tan of x plus 1 over tan of x. I'm almost there. If you look at your identities, 1 over tan of x is equal to cotangent of x. Once this equals that, we're done our proof. In this next example, I'm going to work with simplifying the left-hand side. And although I see a square here and I might consider using my Pythagorean theorem, I also notice that I have a factor of cotangent theta in both terms. So I'm going to factor it out of both terms and see what I have. So when I factor out cotangent theta out of my first term, I'm left with secant squared theta. When I factor it out of my second term, I'm left with minus 1. Now I'm going to take a look at this. This looks like I can use one of my Pythagorean identities. So I can do it two ways. If you can recognize that secant squared theta minus 1 is equal to tan squared theta, you can plug tan squared theta in, or you can replace secant squared theta with tan squared theta plus 1, because that's what it's equal to. And then I still have this minus 1. So this is just equal to tan squared theta. Now, cotangent can be written as 1 over tangent. This is tan squared theta over 1. Cancel a factor of tangent theta into the numerator and the denominator, and I'm left with tan theta, which is what I wanted. So sometimes you'll need to factor. There are some other strategies that we can use when we're doing proofs. I'm going to continue on with those in the next video. So practice some of these ones that use these strategies, and then as you get into ones that are more difficult, take a look at the next video.